So this video begins my next batch of Snap Circuits videos, and this time we're covering the SC300 series. In our last batch we covered the SC100, which was projects 1 through 100. So SC300 consequently gives us 300 projects. And this is the manual that comes with the SC300. So you get the parts that come with the SC100, but you also get the additional parts that the 300 comes with, including the additional projects. So this manual covers projects 102 to 305. And these are some of the new parts that we get introduced to. We get longer snap connections, we get another battery box, we get some more diodes, an antenna, a microphone, and we also get introduced to power amplifiers and capacitors. We also get larger resistors, some integrated circuits, and also some transistors, and some variable resistors and capacitors. Anyway, we are starting off with project 102, which is batteries in series. That's what our circuit looks like, and it's already assembled on the board there. And if you haven't seen my previous video, we're using this Snap Circuits battery adapter or eliminator in the videos. So you're not actually going to see any of these little battery things like this here, because again I'm using that for power supply. Anyway, what this project demonstrates is how batteries in series work. Now in the SC100 we only had one of these, and we knew that it provided 3 volts. Now if you connect it in series, like say if it was right here, what this would do is it would double the voltage. When you put batteries in series, you add the voltage together. It's different from when the batteries are in parallel, but we're not covering that kind of thing right now. We're talking about if they're in series. So in series, you add the voltage up of the number of batteries you have. So we would have 3 volts, and if we had our other battery here, that would be also 3 volts. You add both of them together, you get 6 volts. And that's what our unit is putting out here, is 6 volts. Now in our circuit, we've got R1, which is our 100 ohm resistor. We have our D1 and D2 diodes, light emitting diodes. So we have our red and our new green that we find in the SC300, including our slide switch. So when you turn this on, power flows through, our 2 LEDs light up, and of course a 100 ohm resistor limits the current going to those. Now, because the batteries are in series, we can light up these 2 LEDs. If there was only a single 3 volt battery pack here, these LEDs would not light up, or they would look very dim, and that's because LEDs that are in series like this require more voltage to turn them on. And so, by having 2 batteries in series, we get enough voltage from them being added together that we can activate these LEDs and they'll light up. So that's how project 102 works. So let's do project 103. Alright, well here we are with project 103. It is the Ticking Screecher. There's what our circuit looks like. And here it is on the board. And in this here, again, we're using 6 volts. And again, I don't have the battery here, so we're using our eliminator. We're using our speaker, a photoresistor, and our new power amplifier and capacitor 3, which is a 10 microfarad capacitor. Now the way the Ticking Screecher works is that the power amplifier is amplifying the power to our speaker, so it makes it sound louder. And then, by using the capacitor and our photoresistor, which of course, as we know from the SC100 projects, it adjusts the amount of resistance based on the amount of light that's entering it. So, by changing the amount of light in this, we're changing how quickly this capacitor charges up. And by doing that, it should change the sound coming out of our speaker. So let's power on the circuit and see how this works. See, right now it's kind of making a low frequency ticking sound, and I'm kind of moving it toward the source of the light over here on the right, which kind of changes it. Now watch what happens if I cover the photoresistor up. It charges up the capacitor, and when it's doing that, you hear the sound change. And again, partially blocking it, still lets a little bit of light in. So that is how project number 103 works. So let's move on to project 104. Well, here we are with project 104, which is the Spacey Fan. There's what our circuit looks like. There it is on the board. In this circuit, we're making use of our press switch, our photoresistor, our Space War IC, the motor with the fan on it, our whistle chip, and we are using 6 volts. Again, the battery is not here, so we're using this, and our NPN transistor. Now what this is going to do is it's making use of our Space War integrated circuit to activate the motor, but also play sounds throughout the whistle chip, making use of our press switch and our photoresistor. So if I press the press switch, so you hear the Space War IC sounds through the... Gotta cover that up. You hear the Space War IC sound and the motor come on, as long as it's pressed. Now if I shine a light onto the photoresistor, the Space War IC also comes on, making sound and activating the motor. But here's the thing, the motor is only running at half its power. In order to run it at full power, we have to both have light shining on there and press the press switch. Now the sound may not change as much, but you should notice that the motor is running faster. Now it's getting full power. And again, if I take the press switch away, it goes down in power because only it's going through this now. And our transistor here acts as a switching circuit, turning on and off. But basically, that's how project 104 works. So let's move on to project 105. So here we are with project 105. There it is, right there. It is the two-transistor light alarm. That's how our circuit looks. That's how it is on the board. And in this, we've got 6 volts again. We're making use of L2, which is our 6-volt lamp, along with a 100 ohm resistor R1 and our PNP and NPN transistors. Now right now, as you can see, the light is off, but if I disconnect this jumper wire, the light comes on. Now why does this happen? Well, what's going on in this circuit is current always takes the path of least resistance. So what's going on is that we have our current going through here, through our 100 ohm resistor, and then going through our jumper wire down here, and then back up. So the current is going in this loop here. It is not going through here, through the lamp. But when I disconnect this jumper wire, the light comes on. Because what's happening now is the current's going through this path because these transistors have switched on. Our 100 ohm resistor is connected to the gate input of our NPN transistor. Basically, that tells the NPN transistor whether to switch on or not. And coincidentally, it also tells the PNP transistor to switch on. Now I got a separate video explaining how exactly these transistors work, the PNP and NPN. But essentially, this is telling the transistors to switch on, in which case then the current can flow through here and our 6-volt lamp lights up. And again, when our jumper wire is on, current takes the path of least resistance, and now the current only flows in this loop here, so our light never lights up because our transistors are now switched off. So that is how Project 105 works. So let's move on to Project 106. So here we are with Project 106. It is our light-controlled alarm, and I don't have enough hands here to show it, which looks like that on the bottom. Our light-controlled alarm, that's what our circuit looks like. And here's what it looks like on the board. And this we're making use of our alarm integrated circuit, our photoresistor, which I'm covering up right now, and our NPN transistor, along with our speaker connected to the alarm IC's output. Now, we'll just show what the circuit does when I release my finger here, and then we'll explain why it does what it does. What's happening in our circuit here is our NPN transistor and our photoresistor together are acting like a dimmer switch to powering the alarm IC. Because when I take my finger off, there's less resistance through here, and what it does is it activates our NPN transistor supplying power to the alarm IC, which then gives us the sound outside the speaker. Now, if I were to decrease the resistance more, see, this would actually get a little bit louder if I decrease the resistance with more light. And you can see the volume actually changes because I'm decreasing power to the alarm IC. So that is how Project 106 works. So let's move on to Project 107. So here we are with Project 107. It is the automatic street lamp. And there's what our circuit looks like. And there it is on the board. And essentially the way this circuit is supposed to work is that it mimics the automatic on and off action that you see in your typical street lamp. And what it does, okay, is when we've got light on our photoresistor, see, our lamp does not light up, but as it gets darker, then it lights up. And then as the light comes back, it gets dim and it turns off. So what's happening here is we use our variable resistor to control the amount of resistance between our photoresistor here and our transistors. So what we do is we want the light on there to where this just turns on. So I kind of want it a little bit less, kind of about right there. Okay, so when there is less resistance on the photoresistor, more current goes through our transistor gate, which is our input here. And because of that, it turns on our transistors, but also it acts as a dimmer so we can control how much current goes through there. That's why our light can go up and down in brightness. And of course, when there is less resistance on the photoresistor, then the current just flows through the photoresistor and our transistors never turn on, so our lamp never lights up. So that's how project number 107 works. So let's move on to project 108. So here we are with project 108. It is the voice-controlled rays of light. Here's what our circuit looks like. And there it is on the board. In this circuit, we're trying to control the brightness of our green LED there. Right now you see our red LED D1 is bright, but our green LED D2 is pretty dim. And the way this circuit is, we have our NPN transistor, which is helping control the flow of current through there. We have a 5.1 k ohm resistor and a 100 k ohm resistor connected here across a 100 microfarad capacitor, and here is our microphone. Now if you pay attention to the green LED when I'm tapping on the microphone, you can kind of see it flicker. And that's what we're trying to do. And if you blow, we can make it a lot brighter by controlling the noise coming across the microphone. We're changing the resistance across here, and by doing that we can control the amount of charge across our capacitor, which then changes how much current flows through our transistor, and that's what allows us to increase the brightness of our LED there, because we can allow more current to go around in that loop. So that is how Project 108 works. So let's move on to Project 109. So here we are with Project 109. It is blowing off the electric light. And there's what our circuit looks like. And there it is on the board. And with this project, it's kind of the opposite of what we just did with Project 108, where Project 108, we wanted to increase the brightness of our green LED. In Project 109 here, we're doing the opposite, where with our 6-volt lamp, we want to make it dim and even turn it off. Now right now you see it's constantly on, so we're kind of acting more like a birthday candle here, trying to blow out a birthday candle. And the way our circuit is set up is we've got, again, our two transistors, our NPN and our PNP here. Our PNP is what's controlling the current across our lamp, and we have a 100 ohm resistor connected across its gate to the NPN transistor over here, which then has a 100 microfarad capacitor and a 100 k ohm resistor connected to its gate, and then we have our microphone here and our 5.1 k ohm resistor connected across that. So if I am able to tap on the microphone, you can see I can temporarily put the light out. That doesn't really work so well, but if I blow in there, I can make it flicker. So by blowing there, I can dim it. And if I can really blow on there constantly, I can make it go completely out. And by doing that, again, I'm changing the resistance here across the microphone, which is affecting the charge of this capacitor, which then consequently changes how the current flows through our NPN transistor, and then, of course, controls whether the gate of the PNP transistor gets enough current to light up the light. And of course, if we get less current across the gate, the dimmer the light gets, and then of course if there's no current at all, then the light goes completely out. And again, the charge of the capacitor being affected is what kind of keeps it out for a little while. So that is how Project 109 works. So let's move on to Project 110. So here we are with Project 110. It is the adjustable tone generator. And there's what our circuit looks like. We will also be covering Project 111, which is the photosensitive electronic organ, and Project 112, the electronic cicada. because they both involve the same circuit, just with different parts. So we're doing project 110 again, which is the adjustable tone generator. And this is how it looks on the board. And with the adjustable tone generator, we're making use again of our two transistors, our NPN and PNP. We have a 10K ohm resistor, our R4, our whistle chip, our variable resistor, our D1 red LED, and our speaker. Now when I power on the circuit with the variable resistor set all the way to the right there, our red LED lights up bright, and our speaker doesn't make any sound. But watch what happens with the circuit when I start changing the resistance on the variable resistor. As I change the resistance of the variable resistor, that changes the amount of current that flows through both the NPN and PNP resistors. That's why when you look at the LED goes up and down in brightness as the current changes that passes through the PNP and NPN resistors down through this loop of the circuit. And then, also by changing the resistance, we can change the tone that's emanated from the speaker, which goes through both the whistle chip and the PNP transistor loop. And because it's a tone, it's actually oscillating. So if I was to show you this on an oscilloscope, which I do have, but I can do that another time, we'll actually see a waveform that's going up and down. And as I change the resistance of the variable resistor, that frequency changes. So the waveform peaks will either come closer together or they will spread out. And that, of course, determines the frequency. So the more this goes over to the left, the farther those peaks are. The more I bring this to the right, the closer the peaks are. And that's what, of course, determines the frequency and consequently the tone that we hear out of the speaker. So that is how Project 110 works. So let's move on to Project 111, which is the photosensitive electronic organ, where we change up this circuit a little bit. So here we are with Project 111, the photosensitive electronic organ. Same circuit as Project 110 with the adjustable tone generator, except we've taken away R4, which is our 10K ohm resistor, and replaced it with our photoresistor. And I've moved our variable resistor all the way over to the left for the highest resistance through there. So watch what happens with the circuit this time when I turn it on. See, it's a much lower frequency, but when I move my hand, see, I'm creating a lot more resistance across that photoresistor, and I've lowered the tone so much that you can actually see the LED flashing to the tone, as well as hearing it from the speaker. And as I adjust the amount of light going into the photoresistor, I adjust the resistance there too, and adjust the tone, or frequency, that's being emanated through the circuit. So that is how Project 111 works. Now let's move on to Project 112. So here we are with Project 112, which is the Electronic Cicada. And it's the same project as 110, except that we have the C1, which is our 0.02 microfarad capacitor, over our whistle chip. We've replaced the photoresistor from the Project 111 back with the original 10K ohm resistor. And when we turn the circuit on this time, see, again, nothing's happening, but when I move it down, Now, if you compare the tone between Project 110 and Project 112, you will find that with the 0.02 microfarad capacitor on there, that it is actually producing a lower tone. And again, the tone, these waves are spread out even more than Project 110 is. The reason for that is because we're now charging this capacitor every time it's oscillating, and because of that, there's less current that goes through here, and overall we end up with a lower tone being generated. And again, you can experiment around with it. If we take this off and put C2 on there, which is the 0.2 microfarad capacitor, it'll produce an even lower tone. And again, because it's charging a larger capacitor, which takes more current to charge. And again, that of course results in a lower tone. So that is how Project 112 works, and that concludes this first video of the SC300 series with projects 102 through 112.